this matrix element. What should be the vertex factor? Well, this is we have an electron to start with. In the final state, we will have an electron and also a photon. And remember this full matrix element of a time-ordered product of the full theory. Remember, this was written as the time-ordered matrix element in the non-interacting theory of the same fields. Of course, now the evolution is given by the non-interacting theory. We have, in addition, an e to power I, the interaction Lagrangian. All the connected pieces. So when we expand the exponent, every term will bring, let's say, in our case, the interaction term, we had written it down. This is my interaction term. E times psi bar A slash psi. So here, let me just put I psi bar A slash psi. Now, if I were to calculate this matrix element, okay, I would contract psi and E bar, not E bar, psi and electron in the initial state. That will give me an incoming electron is U. Now, these are matrices. Let me write the matrix components. An incoming electron will bring me a U beta. The psi bar will be contracted with the outgoing electron. Now, the outgoing electron will give me a U bar. This time it's alpha. A will be contracted with the photon. It will give me, the outgoing photon will just give me basically epsilon mu star. What is left is just I gamma mu alpha beta. You see, my Feynman rules already tell me where these come from. And hence, this is my vertex factor. In fact, if I just sum over alphas and betas, this is, I would get U bar I E gamma mu U. So this is my vertex factor. In fact, this is a particular case where I have an incoming electron and an outgoing electron. I could have looked at incoming positron, outgoing positron, outgoing electron, outgoing positron, incoming positron, all those terms. In all those cases, this will be my vertex factor. So basically, my vertex factors are also fixed. That is my, let's say, the fifth rule for each vertex. Introduce I.E. gamma mu. Now look at here. You see, I can go ahead and write this, my interaction vertex, in terms of the spinor indices. That's the correct procedure. But I can take a shortcut. You see, the outgoing particle is all on the left. You see, if I look at this diagram, there's a fermion line. At the end of that fermion line, I have an outgoing electron. The corresponding contribution is U bar. So for an outgoing line, I introduce a U bar. Then I follow the line backwards. I have this vertex. For the vertex, I introduce minus I E gamma mu. Then I keep following the line backwards. I get an incoming electron line. The corresponding term is U. So U bar gamma mu U. If you follow this prescription, go to the end of the fermion line and trace back, well, you get these matrices in proper order for a matrix product. If you are not sure, just write in terms of indices, as I have done over here. And you will again get the correct expression. What would happen, let's say, if I had, well, let me also repeat the procedure for positrons. So I have a E plus. Okay, one thing you should note, I didn't yet put the arrows on the lines. As if you remember when we were looking at the complex fields, we had both particles and antiparticles. For the momentum flow is in this direction. This is K1, this is K2, and this is P. This is the momentum flow. But the arrows on the line, just like in the case of the complex fields, we wrote the number flow of particle number flow. So a particle moving in one direction is an antiparticle moving in the opposite direction. So these are antiparticles. So antiparticle number flow will be, I will show in this way. So these are particles coming into the vertex, but the arrow on the vertex is in the direction of the particle number flow. Antiparticles have particle number -1. So for antiparticles, the particle flow is in the opposite direction as the momentum flow. So what will be the corresponding expression? Let's see, for positron, that positron will be annihilated by psi bar. Now let's see, what was the incoming positron? Incoming positron is V bar. So we have a V bar alpha. Then I have the outgoing positron. Now the outgoing positron is V, but this time it is V beta. This is K1, this is K2. I have the vertex factor, which will be my IE gamma mu alpha beta. Then I have the photon, which give me epsilon plus mu. Now you see, to be able to make these contractions of psi with my fields, let's say, I have to move this psi bar all the way to act on the ket, anti-commuting with the psi field. So I have an additional minus sign there. Because I had to anti-commute the fields. I have to introduce that minus sign. And again, if you look at this line, what is the end of that line? Well, the end is here. So since it's a positron, I have a V bar, K1. I go backwards along the line, backwards in the sense of particle flow. I reach the vertex. In the vertex, I have I times the charge of the particle times gamma mu. And then I keep going along the line. Then I have for the incoming line, the end of the line, let's say I have a V.
Reversing the case, putting minus in front of them, so that the direction will be the same with the incoming and the charge flow with the momentum. So should we put a minus, or is it possible to put a minus in front of K1 in the V?
Wait a moment, we will come to that. It will be possible, because you see, that minus sign cannot disappear. It should come from somewhere, eventually. And that minus sign, in that case, will be, where is it?
Looking for M?
V bar V.
Okay.
So what your friend is saying is, rather than looking at this diagram, why can't I just look at this diagram? Well, the difference, here in this case, my contribution will be U bar minus K1. I start from the end of the line. There's an outgoing electron with momentum minus K1. Then I have IE gamma mu, the vertex here. Then I have U of minus K2. And then, of course, epsilon mu star. And we will see in a moment that, well, they are the same thing. And so any questions about the Feynman rules that we have derived? Now we will apply it to E minus E plus scattering. Well, there are two diagrams we have. This one and this one. Oops, sorry. Let me name the momenta. Incoming are K1, K2, outgoing are P1, P2, K1, K2, P1, P2. The vertices, the photon vertices have, let's say, Lorentz indices mu and nu. So these are the two contributions at lowest order to my electron scattering. Let's say this is the first diagram. This is my second diagram. The contribution to M from the first diagram will be, well, I have two fermion lines. I should start from the end of each fermion line and trace back. So I have an outgoing electron. So that has U bar P1, let's say lambda 1. I have this vertex, IE gamma mu, and I have an incoming electron, U of K1, lambda eta 1. This is the contribution, this is the factors corresponding to this fermion line. I have the second fermion line, this one, which will be, I should start from the end, so I have U bar P2 lambda 2, IE gamma nu, this is the vertex, and then an incoming electron, U K2 eta 2. And then the remaining part is this photon propagator, which will be I over Q squared minus G mu nu plus Q mu Q nu divided by Q squared. This is my M1. The contribution from M2. Again, I have two fermion lines. So let me start with this fermion line. At the end, I have an outgoing electron, so U bar P2 lambda 2. Then, when I went back, I arrived at that vertex. There I have I, E, gamma, mu, and an incoming electron, U of K1, eta 1. So this product corresponds to the factor, to that fermion line. Now I have the other fermion line. I should write the corresponding factors corresponding to the other fermion line. Again, I start from the end. There's an outgoing electron, U bar P1, lambda 1. I have this vertex here, which is I, E, gamma, nu. And then I have the incoming electron, which will have the factor U, K2, eta 2. And again, I have the photon propagator. Let me call this Q prime. Where Q, this is Q prime. Q is P1 minus K1. And Q prime is P2 minus K1. And the total invariant matrix element for the scattering will be M1 plus M2. Now, of course, I will need to evaluate M squared, which will be M1 squared plus M2 squared plus twice the real part of M1 star M2. Let us look at one of them. What is M1 squared? Now, when I'm calculating, remember, look at these terms. And keep in mind that U bars, they are matrices. U bar is a row matrix. This is a row matrix. This is a square matrix. This is a column matrix. So you multiply a row matrix with a column, with a square matrix, with a column matrix of the same dimension. You just get a 1 by 1 matrix, or just a number. So when I'm calculating M1 squared, I should this is a number. I should multiply that number with its complex conjugate. So I should calculate one of the things that I should calculate at least. This multiply by the same thing complex conjugate, because it's just a number. But for a number or a 1 by 1 matrix, complex conjugate is the same as Hermitian conjugate. The transpose is itself.
This P1 or this P2?
Which one? This is P1, this is K1. Now I'm just looking at this term. When I'm calculating the absolute square of M1, I should calculate the absolute square of this term, the absolute square of this term, and the absolute square of this term, and multiply them out. And let me just make a small correction, mu bar. because mu is a dummy index. M1 has the dummy index mu, M1 conjugate will have some other dummy indices.
But if minus one shouldn't be at like relative minus sign.
For the second one, you're right. I forgot to mention that. That is the minus sign that I mentioned before. You see, these two terms have a relative minus sign. Let me write it explicitly so it will be more clear why do we get that minus sign. You see, the matrix element we are looking for is this one, the P1, P2. I will not be writing down the polarization labels. And I have psi bar A slash psi and psi bar A slash psi. This is the second order term, K1, K2. And I should contract the incoming particles with psi's, outgoing particles with psi bars. So I have this contraction plus, okay, let me see. I have that contraction, this contraction, and this contraction, and this one. This is one possibility. The other possible contraction will be let's say psi is contracted with K2, not K1. And psi bar will be contracted with P1. So this psi will be contracted with K1, this other psi. And this psi bar will be contracted with P2. I have two more contractions, by the way, because this psi, what I did was I just changed the contractions of K1 and K2. I could also have changed the contractions of psi bars with P1 and P2. But they basically give me contributions equal to these two. The sum of the other two contractions is equal to the sum of these two. And remember, this is a second order imperturbation theory, so in the expansion of the exponent, we have this 1/2 factorial. So that 1/2 factorial basically cancels this one. So that's why I'm not considering the exchange of P1 and P2. Or in fact, okay, sorry, in the diagrams, I only consider the exchange of P1 and P2. Yes, these two contributions. I have in total 4 contributions. The other two gives contributions identical to these ones, which cancels the 1/2 factorial in the expansion of the exponent. Now, if you look at these things, these terms and these contractions are practically identical if I exchange P1 and P2 in the bra. But P1, P2 is equal to minus P2, P1. There is this minus sign, which is this additional minus sign over here. Or another way of looking at it is, you see, if I want to make this contraction psi bar, well, it's already there. Psi bar and P2, they're already neighboring. I should move this psi bar to P1. So that means I should move it over psi. So this term has one minus sign, if you like. Now, if I look at this one, relative to this one, sorry, relative to that one. If I want to calculate this one, I should move this psi bar all the way here first, so that contraction happens first. And so I have psi bar should commute over two fermionic fields. But if I look at this diagram, in this diagram, this psi bar I should commute it over here, anti-commuting over one fermionic field only.
There will be one minus there in the first one.
You see, there's an overall minus sign,
Uh-huh.
which I just take this one to be positive, if you like. This one corresponding to this diagram, I took that to be positive. The other one had a relative minus sign. So now let's come back to over here. How do we calculate this? Let me look at this one only. This one, u bar p1, gamma mu bar, u k1, conjugate. This is u bar p1, gamma mu bar, u k1, dagger. It's a 1 by 1 matrix, Hermitian complex conjugation and Hermitian conjugation, they are the same thing. But I know how to apply the Hermitian conjugation over matrices, just reverse their order and take the Hermitian conjugate of each one. U dagger k1, gamma mu bar dagger, gamma 0 dagger, u p1. Remember, u bar p1 is u dagger p1 gamma 0. So this is my gamma 0. And u dagger, when I take its dagger, it just becomes u. Now, I will just introduce gamma 0 here. Why do I do that? Well, gamma 0 squared is 1. Remember, gamma mu dagger, well, okay, this product is just gamma mu bar. Because gamma mu dagger, whatever mu is, this is gamma 0, gamma mu, gamma 0. Which is equal to u bar k1, gamma mu bar, u p1.
Gamma
No? No gamma zeros. You see, gamma 0 dagger is gamma 0. In gamma mu dagger, I have a gamma 0 here. That is 1. This gamma 0 cancels with this gamma 0. And this u dagger gamma 0 is what I call u bar. So the effect of complex conjugation in this product is just exchanging the two spinors and nothing else. So let's go back. This is what I wanted to calculate. This is equal to u bar p1, i.e. gamma mu, u k1, u bar p1, now u bar k1, i.e. gamma mu bar, u p1. This is my product. Now, this will be nice. We will simplify it. We have a spinor and its Dirac conjugate spinor next to each other. But I have the same thing for u p1 and u bar p1, but they're on the other ends of this product. So let me just write everything in terms of matrix components.
Also, there was I inside. Into complex conjugates.
Oh yeah, sorry.
So there is a minus.
There's a minus sign over here. So basically I have I minus I, that gave me 1. Now I just wrote everything in terms of matrix components, so this became E squared gamma mu alpha beta, u beta k, u k1 beta, u bar k1 gamma, and gamma mu bar gamma delta, u delta p1, u bar alpha p1. Okay, now this looks nicer because all the spinors and its Dirac conjugates are next to each other. Now what else? I say, there's nothing much I can do after this point. I just have to take the explicit forms of U and U bars, put it over here, and then calculate them. But in general, I mean, when we are colliding electrons, we don't polarize them. It's a half a mixture of positive helicity, half a negative helicity mixture. So rather than calculating this one, let me call this T mu mu bar, lambda prime. Rather than calculating, no, it's lambda 1 eta. Eta 1. Now, rather than calculating this one, what we calculate is, remember, lambdas were the polarizations of the outgoing electrons, etas were the polarizations of the incoming electrons.
UB times U bar gamma.
Okay.
Can you say there is a Dirac delta?
No.
Not Dirac delta, Kronecker delta.
No, this is not a matrix product of U and U bar. You see, we had already seen that U bar U, lambda prime, was proportional to Kronecker delta lambda prime. But that is the matrix product. That is just, you see, here U bar is a matrix. This is just a number. This is, we have alpha is equal to the Kronecker delta, if you like. We don't have that term over here. There will be another simplification. Now, as I was mentioning, this is the scattering of initial polarization eta, final polarization lambda. So initial states usually are not polarized. We have two polarizations. So we average over the initial polarization. And when we put our detector also doesn't usually measure the helicities, the lambdas. So our detector measures both helicities, if you like, or both spin projections. So the cross-section that they calculate, that they measure, will be a sum over all the polarizations. This is usually called the average polar amplitude. Now, this is not the full amplitude, it's just a part of the amplitude, but we are averaging over the initial polarization and summing over the final polarizations. Why? Because the initial particles that we send, they are not polarized. Half of them have one polarization, half the other polarization. So this is why we have that 1/2 over there. And our detector usually measures all of the polarization. It doesn't distinguish between the polarizations, and hence we sum over the final polarizations of the final particles. Why does it simplify our computation? Well, because of this relation. Remember, K1 had polarization eta 1, and U bar K1 eta 1. This is gamma summed over all possible values of eta 1. This is K1 slash plus M. Now, how do we, of course, this is, we have the beta gamma element. Or, if you remove the beta gamma element, sum over polarizations of U K1 eta 1, U bar K1 eta 1, this is equal to K1 slash plus M. Now, how to see that? Remember what U was. Square root of sigma K Xi, square root of sigma bar K Xi. We just, Xi is, whichever helicity you have. So u bar, this will be square root of sigma k xi square root of sigma bar k xi. Well, u bar is u dagger, which will be xi dagger, sigma k, xi dagger, sigma bar k. Gamma 0 is 0, 1, 1, 0, which will be square root of sigma k xi, square root of sigma bar k xi, xi dagger, square root of sigma bar k, xi dagger, square root of sigma k, which will be square root of sigma k xi dagger, square root of sigma bar k, square root of sigma k xi dagger, square root of sigma k, square root of sigma bar k xi dagger, square root of sigma bar k, and finally square root of sigma bar k xi dagger, square root of sigma k. This is this matrix. Now, what is xi dagger? And remember, I am summing over all xi's. This is 1, 0, 1, 0 plus 0, 1, 0, 1, which is 1, 0, 0, 1, which is nothing but the identity. That is the identity matrix. So this is an identity matrix. All these are identity matrices. After summing over xi, this is the simplification of summing over all the polarizations. Now, what will be left? I have sigma, sigma bar products. Well, I had already calculated it, no? Here I already have sigma, sigma bar under the square root is just m. Sigma p is, remember, this is E minus PE plus P. So this is equal to, that sum is equal to, now sigma sigma bar under the square root is m. Here I have sigma k. Here I have sigma bar k. This is m times the 4x4 identity plus k mu, sigma mu, sigma bar mu. But this is nothing, oh, sorry. This is 0. But this is nothing but what we defined as gamma mu. So what this told me is that this product, this sum, is just k slash plus m. So let's go back to our computation. I'm calculating this product. But now I am summing over lambda 1 and eta 1 and dividing by 2. Averaging over the polarization of the initial electron and summing over the polarization of the final electron. This is what I called T mu mu bar average. This is equal to 1 over 2 E squared gamma mu alpha beta K1 slash plus M beta gamma gamma mu bar gamma delta P2 slash plus no P1 slash plus M delta alpha, which became 1 over 2 E squared. Now, if I sum over beta, it is nothing but the matrix element of this, the product of these two matrices. That will be gamma mu k1 slash plus m, the alpha gamma element. But then I have this gamma mu bar gamma delta. If I sum over gamma, it will just give me the product with gamma mu bar, but this time I have the alpha delta element multiplied by this term. But then I have, if I sum over the delta, that's again a matrix product. This time the alpha alpha element of this product. But alpha alpha element is the diagonal element. I'm summing over alpha, so I'm basically summing over all the diagonal elements. So this is just a trace. So what I call T mu mu bar average is a trace of gamma matrices. Now I need to evaluate that trace. Now, trace of gamma mu. Now, in fact, let's say gamma mu 1, gamma mu 2n plus 1. This is an odd number of gamma matrices. This is trace of gamma mu 1, gamma mu 2n plus 1, gamma 5, gamma 5. You remember our gamma 5. It's the product of all four gamma matrices with an overall I. Its square is 1, so this is 1. And it has this nice property that it anti-commutes with all the other gamma matrices. So this is equal to, well, I can anti-commute this gamma 5 over all these 2n plus 1 gamma matrices. Each anti-commutation will bring me a minus 1. So in total, I will have minus 2n plus 1 minus signs but now I can use the property of the trace. This is this gamma matrix, this matrix multiplied by this other matrix is the product of two matrices. I can change the order of two matrices inside the trace. So this will go all the way to the end as gamma 5. Gamma 5 squared is 1. So this is minus trace of So the trace of an odd number of gamma matrices is always 0. Because it is equal to the minus itself, and the only number who is equal to minus itself is 0. And keep in mind that here I have a product of the four gamma matrices, gamma mu 1, gamma 0, 1, 2, 3. Sigma mu nu counts as two gamma matrices. Gamma 5 counts as four gamma matrices. Gamma mu gamma 5 counts as 5 gamma matrices. So just keep that in mind. Okay, so back to our product. T mu mu bar average. This is E squared over 2. Trace. I have gamma mu K1 slash gamma mu bar P1 slash plus M squared trace of gamma mu bar. The linear terms in M is I have, for example, gamma mu times K1 slash times gamma mu bar times M. It contains an odd number of gamma matrices. I'm taking the trace that is 0. So I only have terms independent of M and terms proportional to M squared. Now what are these traces? Well, let's start with gamma mu bar. This is equal to trace of twice G mu bar minus gamma mu bar gamma mu. Why? Because gamma mu bar plus gamma mu bar gamma mu is equal to twice G mu bar. This is my Dirac algebra. This is equal to twice G mu bar. Remember, G mu bar is just 0, 1, or minus 1. So I can take it out of the trace. What remains is this identity, which I will not write again. The trace of identity, of 4 by 4 identity is 4. Minus the trace of gamma mu bar gamma mu which is 8g mu mu bar. Remember, this is inside the trace, the product of two matrices. I can just change their order. So it will be minus trace of gamma mu bar. So I was trying to calculate trace of gamma mu bar. I ended up having an expression minus the same trace. So I can move that minus the same trace to the left-hand side and divide both sides by 2, which will give me trace of gamma mu bar is just 4g mu bar. For larger number of gamma matrices, well, the trick will be essentially the same. You see, K1 slash is just K1 alpha gamma alpha. P1 slash is again just P1 beta gamma beta, if you like. So I need the trace of gamma mu, gamma alpha, gamma mu bar, gamma beta. Again, I will pick gamma mu. I will move it all the way to the right by using the anti-commutation relationship of gamma matrices. So gamma mu, gamma alpha is twice g mu alpha minus gamma alpha, gamma mu. So that trace is equal to twice g mu alpha, trace of gamma mu bar, gamma beta, minus trace of gamma alpha, gamma mu bar, gamma beta. Now this gamma mu bar is twice g mu bar minus gamma mu bar, gamma mu. So the same trace is equal to twice g mu alpha. This trace I had already calculated. It is 4g mu bar beta. So that is an 8g mu bar beta minus twice g mu bar. Trace of what remains inside is gamma alpha, gamma beta plus trace of gamma alpha, gamma mu bar, gamma beta. Again, the same trick. This is twice g mu beta minus gamma beta, gamma mu. So this is equal to 8 g mu alpha, g mu bar beta minus 8 g mu bar, g alpha beta. I use the trace of this, the product of two gamma matrices. Then I have plus 8 g mu beta, g mu bar alpha. I have this term times the trace of, again, product of two gamma matrices. Then minus trace gamma alpha, gamma mu bar, gamma beta, gamma mu. But this gamma mu, I can move to the front, but that is nothing but the initial trace I started with. So I can move it to the left-hand side, divide by 2. So I end up having trace of gamma mu, gamma alpha, gamma mu bar, gamma beta is 4 g mu alpha, g mu bar beta minus 4 g mu bar, g alpha beta plus 4 g mu beta, g mu bar alpha. So this is the trace of 4 gamma matrices. And if you like, if you need at all the trace of 6 gamma matrices, the trick will be basically the same. Just pick the first one, or anyone in fact. Pick the first one, move it all the way to the end using the gamma matrix algebra, and then when you reach the end, just move it back to the front by using the property of the trace. So you will have the trace that you want to evaluate is equal to something minus the trace you want to evaluate. So just move that minus the trace you want to evaluate to the left, divide by 2, and you will get the trace of 6 gamma matrices in terms of traces of 4 gamma matrices, which we already have calculated.
There is no obligation to like a condition like alpha bar equal beta or something.
No.
Okay.
I mean, for arbitrary mu alpha, mu bar beta, this is the trace. Well, if you have such conditions, for example, trace of gamma mu, gamma alpha, gamma mu bar, gamma alpha, let's say, rather than calculating the trace directly, I would use this identity. Twice g mu bar alpha, gamma alpha, minus gamma mu bar, gamma alpha, gamma alpha. This is twice gamma mu bar, but this is 4. minus 4 gamma mu bar. So this is minus 2 gamma mu bar. So that trace is actually minus twice the trace of gamma mu bar, which is minus 8 times g mu bar. So whenever you have identical gamma matrices, by just bringing them together, you automatically reduce the number of gamma matrices you have. So you don't have to go ahead and calculate all the trace of a very large number of gamma matrices. It will be usually simpler. And of course, the easier way will be just to let the computer calculate these traces for you. Okay, let me end here. You see, we didn't yet finish the computation. We just calculated one part of our invariant matrix element. One part of one part, let's say. You see, we didn't even calculate m0 squared yet. So we will continue in our next hour. Any questions before you go?
We still have to fix the Lorentz gauge for the photon propagator.
You see, the photon propagator has 1 minus psi here, or 1 plus psi, if you like. Now psi dependence should disappear at the end. Now once we finish the calculation of the cross section, we will look at the gauge properties, and we will see that that term is actually 0 because of the equation of motion that you satisfy. So will you be here on Monday? Okay. See you on Monday.